welcome to our last podcast on kinetics. This is over section 12.6 called reaction mechanisms. And up until this point in your chemical education, you've always known that in chemical reactions you get something like this. All right, and you can balance an equation, and you guys can predict equations or predict products and all that. But it turns out that reactions actually happen through a series of steps, and usually the final balanced equation is a culmination of a number of those steps. So there's three kind of steps that we're going to see. The first one is a unimolecular step, and that's where you get some kind of decomposition. So you get reactant A breaking up into products. And if that was a rate law, if we were to look at that, you'd see over here that the rate equals K times the concentration. So this is a first order reaction. Now in a bimolecular reaction, or one with two steps, or I shouldn't say two steps, but two bumping ins, you get A bumping into A or A bumping into B. And either way, when that happens, you get an overall second order reaction. You could, of course, see the 2 up there. And then you know that there's a 1 right there. So those are second order. And then the third one, and this is pretty much probably the rarest of them, you would have 3 things bumping into each other to make a reaction go. So imagine A plus B. And that would give you an overall third order, or A plus B plus C. Now the reason that would seem kind of odd, because if you can imagine, here's some A, and it's going to crash into maybe, here, let me get a different color, into B, but at the same time, C's got to also be bumping into it. All right, so that's not going to happen very often. I mean, you think of maybe you're driving in a car. How often does it happen that 2 cars bump into each other? Well, that's usually what a wreck is. But how often is it going to be that you get 3 cars bumping into each other at the same time? So these are the kind of elementary steps that occur. And again, termolecular is probably the most, is the rarest of them. All right. Now, when we do these reactions, or when we see a reaction, we've got to figure out, one, how many steps there are, and which of those steps is going to decide on how what kind of runs the reaction, so to speak. All right, and what happens is if we look at a reaction that has multiple steps, it's always going to be the slowest step that determines how fast it's going to go. And as you can imagine, let's picture we're building a brick wall, right? And again, I apologize for my artwork, but you guys. Now this brick wall is up a hill, and over here we've got some guys. This is some awesome art here, and we've got a wheelbarrow, right? And we've got some bricks. So we've got a guy putting, let's say he's putting these bricks into the wheelbarrow, and then we've got another guy that's going to wheel the barrel up the ramp, and then we've got a third guy that's up here, and he's going to go ahead and build the brick wall. Well, if we look at that, we can say that kind of takes place in 3 steps. We've got the guy that puts the bricks in the barrel, the guy that wheels the barrel up to the ramp, and then the guy that builds the wall. Now, of those 3, which do you suppose is probably the slowest step? Well, I'm just going to say that I think this step right here is going to be the slowest. The guy carrying the bricks all the way up the ramp, this guy could put them on pretty fast, and this guy just dumping them in there is going to be a little faster. So this whole reaction, if you think of it that way, is going to kind of be determined by how fast this guy can carry all those bricks up that ramp. And so that is the rate determining step. And I don't know if that helps you or confused you, because I know my artwork's pretty poor, but I did my best, right? So let's look at a reaction that we have right here. Now we've got some nitrogen dioxide, carbon monoxide, producing nitrogen monoxide and carbon dioxide. If we look at the data from the experiment, we could figure out the rate law to be this. So it's a second order with respect to NO2. And so it turns out that occurs in 2 steps. And we call those steps elementary steps. So 2 steps. Okay. So first what happens is NO2 bumps into another NO2, and that makes some NO3, nitrogen trioxide, and some nitrogen monoxide. And that turns out to be a slow step. And then an NO3 bumps into a carbon monoxide, and that makes NO2 and CO2, and that's the fast step. Well, which step is going to determine how fast this reaction is going to go? Well, it's going to be this step, the slow step. And so if we look at the rate law, the rate is determined by NO2 twice, and that's exactly what we get right there. Okay, NO2 bumping into each other. Now, what about some of these other things that we have here? Because look at this. Here's our overall reaction right here. Notice there's no NO3. There's no NO3 in that whole reaction. But we find it on both sides of the equation here. And then, is there anything else you don't see? Well, let's see. Nope, that's it. So, basically, these are on either side, so they cancel each other out, right? And actually, it turns out that this one of these NO2s cancels out there. But the ones that, the components that are there before and after the reaction, pardon me, I'm saying that poorly. The components that are part of either the step, but they cancel each other out, we call those intermediates. All right? And you'll see questions where they'll ask you what the intermediates are. But it always works the same. Excuse me. Intermediates are made, and then they're consumed. And when it's all said and done, if we were to add all this up, like Hess's law, we would go ahead and get that reaction right there. All right. So knowing what we know now, let's look at a typical problem that we might see out of a textbook. Okay. So we've got this reaction right here. And go ahead and pause the video. Again, if you want to try the problem, go right ahead. But just read the reaction for a second and see what we're going to be doing. Now, this asks you, what is the molecularity of each step? Now, if you're asking yourself, what in the world is molecularity? Well, that's this stuff right here. They're asking you, is it a unimolecular, bimolecular, termolecular, that kind of thing. So if we want to look at the molecularity, well, right here, this is a unimolecular, bimolecular, bimolecular. All right, so we've answered that question right there. And then the next question, what is the rate equation for the third step? What is the rate equation for the third step? Okay, so I'm just going to write out the rate law equation, right? Our rate equals K times, and if we look at this, the third equation right here, we've got the concentration of N2O times the concentration of H2. And according to that step, okay, it's first order for each one of them because there's only one bumping into each other. So that would be the rate equation for that step. And then this last one, show that the sum of these elementary steps give the net reaction. Okay, so up here is our net reaction, right? And just like our Hess's law stuff, of course without all the delta H's over here, right? We don't have to worry about that. We've just got to cancel out things that appear on both sides. Those things that we call intermediates. So let's see. N2O2 is produced there. Notice it's consumed right there. Let's see. N2O is produced there, and it is consumed there. And then let's see if we got everything. Okay, that gives us 2 NOs, 2 H2s, N2, and 2 waters. So that right there is the whole reaction. Right, so there you have it. So what we want to look at next is the kind of questions that we get on an AP test where they are asking you, is what's a valid mechanism based on these elementary steps. And so there's a few things that we've got to be aware of. The first fact is that if you get a reaction mechanism like the one we just looked at, it's got to agree, the balance equation has to agree. Okay, so that has to happen. And what I mean by that is if I were to go ahead and look at our last problem, all these steps agreed with this balance equation and agreed with the stoichiometry. The next thing that's important is that it's got to agree with the experimentally determined rate law. All right. And we haven't done a problem like that yet, but we're going to in just a second. And so if you look at all the steps and we find the slowest step, that slowest step has to agree with the rate law. If not, then it's not a valid mechanism. And then there's something I highlighted here. This very important stuff right here. Okay. And it's something that we need to just kind of keep in the back of our mind, that a balanced equation does not tell us how the reactants become products. In the past, I've mentioned to you there are side reactions and things like that, and that's why we don't get 100% yield. You just have to be aware of that, the balanced equation is a summary of the overall process, and that overall process might have 2 elementary steps or might have 3 or 4. So let's look at the kind of problems, or let's look at another problem and see if we can figure it out. All right, so here we have another reaction. Now it looks like we have 3 elementary steps. All right, so for the first one, it says, what's the overall stoichiometric equation? So again, you just kind of treat it like a Hess's law equation, and you do some canceling out. All right, so I've got, let's see, I want to look for things on both sides. So I've got some NH2Cl, got some of that over there. Let's see what else I have. I've got some N2H5 over here. I've got it over there. It looks like I've got some OH on this side. I've got some OH on that side. And again, there's no coefficients in front of them. If there were, then we would have to account for that. And let's see if I've got anything else. Okay, it doesn't. I think we're good. So the overall reaction for that thing would be NH3. And, oops, and there's 2 of them, right? So I better put a 2 there. Plus OCl minus. And that is going to yield some N2H4 plus Cl minus plus water. All right, so let me just do a quick check. We got 6 H's, 6 H's, 2 N's, 2 N's, 1 O. There we go. So there is our overall stoichiometric equation. So that's what's going on, and that looks like a pretty straightforward answer. Okay, which of these 3 steps is rate determinant? So all I would do there is I'd go, well, step 2 is, because that is the slow step. And again, it's just imagine that's the guy in the wheelbarrow, carrying all those bricks up that ramp. So step 2 is our rate determining step. Write the rate equation for the rate determining elementary step. Okay, so this is our rate determining elementary step right here. But we have a little glitch. Look at our rate determining step. Now, in this step, we have an intermediate. Now, an intermediate cannot be part of our rate expression because our rate expression has to agree with the stoichiometry. All right, so if I were to write out the rate expression for this, I'd go rate equals K, and then I've got to put my concentrations in brackets. I know ammonia is there, but how do we get NH2Cl? Well, we get NH2Cl when these 2 guys bump into each other. All right, so that has to happen to get that, and then we also need another ammonia. So what we have is we have ammonia, and I've got to put a 2 there because 2 of them are going to bump into each other, and then an OCl minus. All right, so that's our rate expression for the rate determining step. Kind of weird because you have to do a little substituting. It'd be really nice if it was just this first one with no intermediates and we could just put NH3OCl, but it doesn't work that way. And then what reaction intermediates are involved? Well, we've already done that. We've got this as an intermediate, right? This thing is an intermediate. And OH is also an intermediate. So there are 3 intermediates in that step. All right? How's that seem? Look confusing? Hopefully it's not too bad. So let's go ahead and do one more, and then we'll practice these in class. We've got a whole bunch of them we could practice in class so that you can get a good feel for it. All right. Let's look. Oops. Uh-oh. Looks like I've got a slight... Okay, fixed it. So let's look at this. Show that the three elementary steps add up to give the overall stoichiometric equation. Okay, so what I'm going to do there is basically identify the intermediates, right? So I'm going to answer D in that respect. So I've got H2O on this side is being produced, and nope, it's not there. So what about, oh, here we go. OI, that's being produced and being used. HIO is being produced here, being consumed there, and I believe that is everything, right? Yeah. So if I were to write this out, it looks like it would be something like this. Hydrogen peroxide plus H plus. Oh, we got ourselves a redox here, right? Plus, oops, and look at this. Were you telling me to put 2 there? Oh, I'll put 2 there. Oops. Oh, let me erase that. That's horrible. Appreciate the help. All right, plus 2 H plus, right? And let's see, we have anything else? Oh, we have some I minus. Oh, look at this. So I've got plus 2 I minus. All right, so there are my reactants. And then let's look at my products. I've got water. I've got 2 waters, so that yields 2 waters. And then, let's see, some iodine. And I think that's it. I2. So let's just do a quick check. 2 I's, 2 I's, 4 H's, 4 H's, 1 O. Okay, great. Balance, we're balanced there. Okay, great. So, yeah, so that's it. Okay, so there's our equation. What's the molecularity of each step? Okay, well, there's 2 things bumping into each other right here. We'll call that biomolecular. 2 things, again, biomolecular. And then look at this. 3 things, termolecular. Question C, for this mechanism be consistent with the kinetic data, what must be the experimental rate expression? Well, let's go ahead and write that out. The rate equals K times, now which is our rate determining step? Well, it looks like it's this one, right? So for this to be our rate determining step, we've just got to have a hydrogen peroxide bump into an I. So H2O bumping into an I minus. Okay, so that wasn't too bad. And then last, the intermediates, we've already done that. Okay, so those are the kinds of questions you get. It's important that you realize that the slow step is always the rate determining step, and that you can do a little Hess's law and combine all those reactions to get the overall balanced equation. So we'll practice these in class, and if there are any questions, like